Hello and welcome to another power electronics class. In the previous class, we started the buck inverter. We spoke about how we design and build a buck converter and different characteristics of a buck converter. A buck converter, as you know, is to step down a DC voltage. It has a switch, an inductor, and a capacitor. We also analyzed the buck converter to find the current ripple, delta IL. Also, we analyzed it to find the output voltage and the ripple of the voltage as well, delta V out. And we solved one quiz, one practice problem. The beginning of this class, we had a quiz with our in-class students. I would post the quiz for the online students as well after this video is posted, and you would have a week to take the quiz. We're going to have an upcoming exam next week, and I would have a review session on Wednesday. And next weekend, I would post the exam for the online students. And I would also send an announcement about the details of the exam, the first exam as well. Today, we will continue with the buck converter, the modeling and the analysis in real time of the output and the input and the output voltage and the current. This is an example of a PSPICE modeling. And the output looks like this. The red indicates the inductor current. The green is the capacitor current. And the blue one is our voltage, the switching voltage of the capacitor and the inductor. So you can see that, and I would show it with an example of video. I found a very good video that shows the step down applications and the operations in steady state. We have two videos. I'm just going to play the second video because I think it's very useful to visualize how a buck converter works. And I would highly recommend that you watch the first one as well. That one also shows you a practical example and a simulation of a buck converter. So we will continue with this and finish buck converter. Next, we would start with the boost converter. And after that, if we have time, with the buck boost converter.
Down AC voltage. We use a transformer, but how do you step down DC voltage? We use a buck converter. What is a buck converter? In this video, we will be exploring the design process and working of a buck converter, which is used to lower the DC voltage efficiently. If you have a source, let's say DC, and a switch that is turned on and off periodically, you get a PWM signal. The amount of time a digital signal is in the active state relative to the period of the signal is called its duty cycle. If the switch is on for a long duration, the duty cycle increases, and if it's on for short duration, the duty cycle decreases. Now, if you calculate the average voltage of a cycle with duty cycle 50%, it's half of the input voltage. That is, we have reduced the voltage from 12 volts to 6 volts with just a switch. For efficiency reasons, we will replace it with an electrical switch or a MOSFET. This MOSFET is controlled by a PWM signal. How the PWM is generated and controlled will be explained later in the video. But this is just the amplified PWM signal, and it has high voltage peaks. To smooth this, we add an inductor in series with the load. This is an inductor. Inductor wants to keep the current constant through itself, and for that it will instantly change the voltage across itself. As the switch closes, the current starts to flow. To resist this flow, the inductor drops the voltage at another end to zero, creating equal and opposite voltage to the battery. This is possible due to the magnetic fields which are generated in the inductor. but it can't resist it for a long time, thus the current starts flowing and voltage at the other end starts rising. Also, the inductor starts storing the energy in its magnetic fields. After some time, the magnetic field stabilizes and the inductor will act as a closed switch, allowing maximum current to flow. Now, if you open the switch, then there is no source to supply current and thus current starts falling. But as you know, current through the inductor cannot change instantly. Hence, now the inductor acts as a battery supplying current, but it slowly runs out of energy. As this end is open, the electrons accumulate here, creating a high negative voltage. This may damage the components. Thus, we add a low voltage drop Schottky diode to create a path for electrons. But the voltage at the load still has high voltage spikes. Hence, we increase the frequency of the PWM signal such that the voltage and current by the inductor remain somewhat stable. This is also the reason why the switch mode power supply uses high frequencies. To further smooth out them, we add a capacitor in parallel. This is a capacitor. Capacitor wants to keep the potential difference constant across itself, and for that it will change the current through it. As the switch closes, the voltage increases to 5 volts. To resist this, the capacitor flows current through itself, raising the other terminal to 5 volts. This is possible due to the electric fields which are generated in the capacitor. But it can't flow current for a long time as the plates get charged, thus the current reduces and voltage at the other end starts dropping to the ground. Also, the capacitor starts storing the energy in its plates. After some time, the plates get fully charged, thus no current can flow, and the capacitor acts as an open switch. Now, if you open the switch, then there is no source to supply voltage and thus voltage starts falling. But as you know, voltage across the capacitor cannot change instantly. Hence, now the capacitor acts as a battery supplying current, but it slowly runs out of energy and thus the flow of current reduces, and after some time it stops, thus the voltage drops. And we have created as the buck converter. But there are some issues. As the load changes, the voltage across the load also changes, so we need to create feedback to change the duty cycle of the PWM signal with respect to the load. Also, how is this PWM signal getting generated? This is the complete circuit. The voltage at the output is reduced by a voltage divider and it is fed into an op-amp which acts as an error amplifier. This component is known as an operational amplifier, or an op-amp in short. It has 2 inputs and 1 output. The other 2 terminals are for the supply voltage. It is used to amplify the difference between the inputs. It compares both the input. If the voltage at the non-inverting input or the positive terminal is greater than the inverting one, then the output is the positive supply voltage. Or, if the voltage at the inverting input or the negative terminal is greater than the non-inverting one, then the output is the negative supply voltage. In this configuration, the op-amp wants to keep both of its inputs at the same voltage, and for that, it will change its output. As the feedback is to negative input, the output varies according to the voltage at the negative input. This can be seen as a seesaw. When the input voltage falls, the output rises. And when the input rises, the output falls. This is how the differential amplifier works. This is a triangle wave generator. The output of the error amplifier and wave generator is fed to another op-amp which acts as a comparator and outputs the PWM signal, which controls the MOSFET. Here the negative input is a constant voltage from the differential amplifier and the positive input is the wave from the triangle wave generator. Hence, when the triangle wave is higher than the constant voltage, the output is the positive supply voltage. Here it is plus 5 volts. And when the constant voltage is higher than the triangle wave, the output is the negative supply voltage. Here it is ground or 0 volts. This is how the comparator works. The constant voltage increases, then the width of on time decreases, and if the voltage decreases, the duty cycle of PWM also decreases. This is a P-channel MOSFET. An N-channel MOSFET will turn on when the gate voltage is above the source voltage, and a P-channel MOSFET will turn on when the gate voltage is below the source voltage. So when the PWM is high, the MOSFET is off, and when the PWM is low, MOSFET is on. Hence, the duty cycle of PWM and MOSFET are opposite. As one increases, other decreases. But you may think, why not use an N-channel MOSFET? Because it is on when the gate voltage is high and off when the gate is low. Because the voltage at the gate required to turn on the N MOSFET should be higher than the source voltage, and during operation, the drain and source voltage will be almost the same. Thus, we need higher than VCC at the gate to turn on the MOSFET. Hence, we use AP MOSFET. Also, we add a pull-out resistor between source and gate. This is the positive supply from the battery. These voltages are created with the help of voltage regulators. As these voltages are used only for references, thus there is no current drawn from them and no power is lost. In real cases, due to non-ideal components, some power is lost as they draw a small amount of current. Now, let's look at the working of the complete circuit. We will have an input voltage of 12 volts, and we want the output of 5 volts irrespective of the load.
Diabetes.
Coronary diseases, the answer.
Pretty much all chronic diseases of the Western world are associated.
Now, if we increase the load, the current increases, but the PWM is the same as before, hence the voltage falls. This causes the voltage at the reference to fall and thus increasing the difference between this and reference at the differential amplifier. This increases the voltage at the output, and then the duty cycle of PWM decreases from the comparator, thus increasing the on-time of MOSFET and increasing the voltage at the load. Also, we can change the voltage by changing the value of the potentiometer. This change in resistance will affect the feedback voltage, thus it will change the output of the error amplifier and then change the PWM signal. Now, while designing this, some care should be taken. First, the voltage of the error amplifier should always be below this reference voltage. Hence, we select the feedback voltage divider such that the voltage does not exceed 2 volts. Thus, the resistor value turns out to be 100 kilo ohm and 20K trimmer. But this will reduce the voltage to a minimum of 6 volts. Hence, we use a 100 kilo ohm trimmer. For this arrangement of the op-amp and the value of the resistor, the minimum output voltage is nearly 4.5 volts. For these values, if the load is reduced by a large amount, the reference voltage may rise above 2.5 volts as the energy storage components release their energy. This isn't an issue with this analog circuit, as the error amplifier will output 0 volts and this will turn off the MOSFET. But for a digital PWM controller, this may cause some problems or damage them. The second is the inputs of the comparator. In this arrangement, we get a range from 12 to 5 volts for this feedback resistor values. And if the inputs of the comparator are reversed, then the range becomes 8 to almost 0 volts. Also, the high voltage output is towards the high end of the trimmer. This is how the closed loop buck converter works. The voltage and current from the source are converted to lower voltage and higher current at the output. Thank you for watching.
How do you get a brand new ACD system across the panhandle from just net?
Okay. So that was a illustration of how a buck converter works. We already mentioned all the components, the competitors, how we generate the signal. By the way, the triangle signal could be generated using what we call a crystal frequency generator, or we can use a something like a 555 timer. I don't know if you had LIC with me. At the end of LIC, we speak a little bit about the 555 timer. And by controlling the duty ratio, the duty cycle, we can control the output voltage of a buck converter. So that concludes the buck converter. Let's start with the boost or setup DC-DC converter. So for a buck converter, the inductor was on the other side of the switch. For the boost converter, it's at the input, we can say, on the left side. So one way to memorize it, if you see these immediately, if the inductor is on the left side of the switch or the transistor, it's a boost. And for a buck converter, if we go back to the buck converter, you can see that the inductor is after, we can say, the switch. So what is a boost converter? A boost converter steps up the voltage. So the output voltage is greater than the input voltage. As I mentioned before, we can't use a transformer to boost the voltage of a DC signal. It doesn't work. So what we can do is technically what this does is when we are using a switch, we are converting the DC to AC, and using the magnetic field that is generated in the inductor. It technically, you could say, not exactly, but works like a transformer. So what we are doing, we are converting the DC to AC. This is a better way to learn it, and then we are boosting up the voltage. And you can see that when the switch is on, then the inductor would be directly connected to the negative. So you have a loop over here and the current goes this way. And when the switch is off, the current goes through the inductor, through the diode, and into our capacitor and starts charging the capacitor. The principles are the same as what we had in the buck converter. The inductor is for storing energy using its magnetic field in terms of the current, and capacitors are very good at storing the voltage. And we also know that when you connect the capacitor to a voltage source, initially the current spikes because there will be a high current passing, so the capacitor would charge, and when it's fully charged, it acts like an open circuit, doesn't allow any current to pass. And for the inductor, it's the opposite. So initially it resists the increase of the current, therefore the voltage spikes, and then when it's fully charged, it's going to act like a closed circuit, and the current is constant between it, and the voltage on it would drop to 0. So this shows the voltage conversion ratio. Again, the same thing that we had for a buck converter also applies here for duty ratio, but here for the output voltage, we have a different equation. For the buck converter, V out was dVn, D was the duty ratio. Here, V out over Vn is 1 over 1 minus D. In other words, Vn is equal to 1 minus D V out, or V out is equal to Vn over 1 minus D. And D is our duty ratio. Again, when the switch is on, I'm going to write it up here. You can see that the charge is going up, especially in the capacitor. And then we have off, and again we have on. And the voltage, you can see that initially when it's connected, the voltage jumps, and then the voltage reverses back. The same things that we had for the buck converter. Ts is our period, which is equal to T on plus T off. And here you can see that 1 minus D Ts gives us the portion where we have the voltage converted. So the voltage output is going to be Vn dTs, which is V out minus Vn times 1 minus dTs. And when we simplify this, we get to this equation, or the equations that I already mentioned. Only equation that is very important is this equation to keep in mind. So this was the output voltage to the input voltage ratio. And the inductor's current ratio looks like this. We would assume that we have an ideal system, and in an ideal system, the input power is equal to the output power. And as you know, the input power is Vn In, and the output power is V out I out. I out, according to the Ohm's law, is V out over R. Therefore, IL, which is equal to In, is V out over Vn I out. again using the Ohm's law. And we know that V out over Vn is 1 over 1 minus d. So we're going to have I out over 1 minus d. In other words, when we again convert it using the Ohm's law, we're going to have V over 1 minus dr. Now to get the peak value, we need to calculate the slope. We calculate the slope using the derivative equation. So dilt over dt is going to be VL over L. In other words, because it's an ideal situation, VL is equal to Vn. So we can write it at 2 delta IL, the same thing that we had. I'm going to show the graph in the next slide. Would be Vn over L dTs. Therefore, delta IL would be Vn over 2L dTs. Now, for the capacitor voltage, again, we can use the derivative. Here we have the charge, and we can find, again, as you know, dVc over dt gives us IC over C. Or we get this from the charge Q is equal to CV, and then we can find the charge, which is dQ over dt, and we can get to this. So to get the peak value, we again calculate the slope, because we need to find where the slope is actually equal to 0 and it changes direction, and we can get the peak value. So it's going to be dVc t over dt, which is IC of t over c, which is going to be equal to negative V out over RC, which gives us the slope. Now, negative 2 delta V is equal to negative V out over RC dTs, which is delta V would be equal to V out over 2RC dTs. Now, how can we reduce the ripple and the delta? We can increase R or C, and therefore we can reduce delta V if we want to reduce delta V. And same thing for delta I as well. We can increase L, so we can increasing L decreases the delta IL. So this slide shows all the equations for boost converter operations. And please write it down. I'm going to solve a practice problem. Again, V out over Vn is equal to 1 over 1 minus d. And delta IL is equal to V out minus Vn over L times 1 minus d Ts. And Vn is V out, I out, and IL is 1 over 1 minus d V out over R. So another comparison between a buck and a boost converter. For a boost converter, again, you can see if you move the inductor to the other side, this is the easiest way. If you see the inductor at the input of on the left side of the switch transistor, that's a boost. And if it's on the right side, it's a buck. The other indicator obviously is that the capacitor in a boost converter is in parallel with the source and drain of the switch, or the emitter and collector of depending on what type of switch we have. We can replace this switch with any type of transistor or switch as well. So first example, the duty ratio is 0.4. The input voltage is equal to 12 volts. What would our output voltage be in a boost converter? Perfect. So using the equation, V out would be equal to Vn over 1 minus D, which is 12 over 1 minus 0.4, gives us 0.6. So the output voltage is 20 volts. So we went from 12 volts to 20 volts. Now, if the inductor is, oh, let's find something else. If the input power is 60 watts, I want you to find delta IL. What is a ripple current? Or let's find the IL, the inductor's current. Sorry? Yes, the same. Yes, you can use this equation. Did you get the answer? Yes? Okay. So as we know, Pn is equal to P out. So Vn In is equal to V out I out. Okay. So if Pn is 60 watts, In would be equal to 60 over its voltage 12, gives us 5 amps. I would immediately know that IL is equal to In, which is 5 amps. I don't even need to calculate it because it's an ideal situation. But if I want to use this equation, IL, and let's find I out as well. I out is equal to P out over V out. Am I correct? So what is V out? It's equal to Vn. It's 60. And what is V out? V out was from the previous, we got 20. So this is going to be 3 amps. Yes? So IL would be V out, which is 20 over 12, times 3, 20 over 12. If you multiply it by 1.66 something, yes? If you multiply by 3, gives you 5. Or in other words, I can do it like this as well. I can use this equation. I out, which is 3 amps, over 1 minus D. And what is our D? It's 0.4, so 3 over 0.6. Which gives us again 5 amps. Is it clear? Yes? Okay. So IN is equal to IL. We didn't even need to do that, but I wanted to just show you that because the system is ideal lossless. Obviously, this doesn't apply in real world scenario. So in a boost converter operating in continuous conduction mode, increasing the duty ratio decreases the output voltage to the input voltage ratio. Is it true or false? Again, V out over V in, going back to the equation, is 1 over 1 minus D. V out over V in is 1 over minus D. Is it true or false? Yes. So if you increase this, what happens to the denominator? It decreases. The denominator decreases. And when the denominator decreases, what happens to the... Yes, it increases. It says here it decreases, but it's not. It actually increases. Okay. Thank you. Okay, another clicker quiz. I think, yeah, we can do this and then we can call it a day. So a boost DC-DC converter is operating in a DC steady state under the following conditions. Vin is 5 volts, V out is 12 volts, P out is 30 watts, and the frequency is 200 kilohertz. The value of the inductor is selected such as that under these operating conditions, the peak-to-peak ripple, delta IL, is 2 amps. What is the value of the inductance L in microhenry? Again, I'll give you 5 minutes to think on this. It's going to help you a lot. On the exam, you're going to have something exactly like this. Do you want me to go back to the equation sheet or do you? Okay. Perfect. Great. Thank you. Remind me to give you extra point on your exam. So to find this, we first need to find the duty ratio. The duty ratio V out, already know that V out is equal to Vn over 1 minus D. Therefore, the duty ratio D would be equal to 1 minus Vn over V out. 1 minus 5 over 12, which gives us 0.583. Now, the inductor ripple, when it's in boosting and during the on cycle, delta IL is Vn, according to the equation, over L dTs, and Ts is equal to 1 over Fs. So let's find Ts is 1 over Fs, which is 200 kilohertz. So 1 over 200,000 gives us 5 microseconds. Now, microseconds. Now, let's solve to find L. L, according to this equation here, I think I had L, yes. Can find it from here as well, or from this. L is Vn dTs over delta IL. Again, multiple ways to solve it. This is one way. It's going to be 5 times 0.5833, which is our D, times 5 times 10 in the power of -6, which is our duty ratio, divided by IL, delta IL, again, delta IL. If we want to calculate it, Vn, which is 5, oh, I forgot to mention, we already have delta IL, sorry, 2 amps. So it's going to be over 2. This is equal to 7.29 times 10 in the power of -600. In other words, 7.29. Okay. Now the PSpice modeling for a boost converter looks like this. Again, you can see we have the switch, we have the pulse width modulator, a signal generator, and again, in real world, this is actually an op-amp competitor, and we have the voltage source for that. We have the inductor, as you can see, on the left side of the switch. We have our diode, and we have the capacitor in parallel with the load and also the switch and the diode. So if you want to model this using PSpice or any other model tool, you can use a switch, you can use a pulse width modulation signal, and you can change this frequency manually, and then you can have the voltage source connected to it. Now, the simulation results look like this. Again, the red is the voltage, and the green shows us the inductor current. And you can see that it's boosting the current. And this is, I think it's for a 50-something%, more than 50%, like around 60% duty ratio. Okay, so we covered the boost or step-up DC-DC converters, and the applications, and also the operation and steady state. The next type of converter that we would cover, we'll cover this next week, is the buck boost converter. Our first exam is up to this point. The buck boost converter is not in the exam, it's anything up to this point is going to be for exam number 1. So the exam number 1 would be at the end of slide number 38. Okay, that's it for today. I don't think we have enough time to cover Buck Boost, and I would see you on Wednesday. Again, we're gonna have a review session on Wednesday, and for the in class, we have our first exam next week, and I will post an announcement for the online students. Thank you so much, and see you on Wednesday.